Periodic table today. As far as how the folding works on this today, let's see here how this is set up. All right, the front cover is going to be this one right here. This will be the front cover. This will be the front page right here. And then if you want, you can go ahead and tuck in this page into the middle of your booklet. So they kind of all go together. So again, front cover looks like this. Back side should have these two tables. That's kind of how we'll go about going through them here today. And you do need another copy of the periodic table because we will be writing on them again today. All right. Last class. Now because I'm teaching so darn many sections, I forget where we got where. This is what I wrote down, but I don't remember if we actually got through this or explained it in this particular class. Did we talk about the difference between paramagnetic and diamagnetic?
Yes.
Okay. If it's paramagnetic, we have unpaired electrons. If we have diamagnetic, all the electrons are paired up. Okay, so and to me the name doesn't make sense because if I think of paramagnetic, para sounds to me like paired. All right, so unfortunately it's just the opposite here, and so paramagnetic is actually have unpaired electrons. But now this is not the type of magnetism that you normally think of when you think of magnetic things. Anybody know what the name of the magnetism is that you normally think of?
Electromagnetism?
Well, electromagnetism is one of them, but we have to add some electricity. How about just plain old magnets that don't have any electricity running through them?
Like ferromagnetic?
Ferromagnetic, yeah, that's called ferromagnetic. And so that's called ferromagnetic.
So
and what's
just a totally different thing.
it's a totally different thing. Ferromagnetic. And here's what ferromagnetic is. If we have a ferromagnetic substance, this is one that has unpaired electrons. That have their spin aligned. And I don't know enough about magnetism to get into the great details of how we make other permanent magnets, but obviously it gets its name because ferro is from iron. Okay, ferrum is the Latin name for iron and is the property that corresponds to what we observe with iron. And this, of course, when we have ferromagnetism, these here have a strong attraction to a magnetic field. So that's a new piece we add on here today to the different types of magnetism. All right, so now this is going to take us into our packet, and I did the best I could with the photocopying here today. I took some figures from your text and had them copied, and I know that some of those numbers in text did not show up so well. If you do have your textbook handy, it might be convenient for you to open up your textbook, then you can see the colored version of it. It'd be easier to see those numbers and such standing out. But when we've talked about electron configurations up to right now, we've talked about how we would determine them based on the building up principle. So now if you look through these, look through them and see if you can find any electron configurations that don't match what we predict. I'll give you about 1 or 2 minutes here. Just go ahead and circle them and then compare with a neighbor. See if you can find some electron configurations that do not match what we would predict based on the building up principle. And again, once you find them, compare with a neighbor. And if you have no idea what you're looking for, have your neighbor help you. find some electron configurations that don't match what we would predict from the building up principle. If you came in late, there's handouts back here. We're doing periodic tables again today. A little bit in my copy. You can see it. It's easier to see in color though. All right, compare your answers with the neighbor. See if you've found some on there. And if you don't have the same ones, line them up.
Yeah.
Okay, let's have some atomic numbers. What's one atomic number?
41.
41. Where are we at? Right here. What's another one?
47.
47. What's another? 24. What's another one?
29.
29. Okay, how about 46? Any others in here? 45 and 44. 79. 78. All right. Okay, now here's what I want to tell you about these, and there's more. In fact, if you go and look down in here, you're actually going to find that there's probably more exceptions to the rule than the rule. And this goes for a couple reasons. First of all, we talked about in here, remember what happens the further away we go from the nucleus?
More energy.
There's more energy, but what happens to those energy levels?
You start getting all mixed up.
They start getting mixed up, but they start getting also closer together. And each energy level has one more sublevel. So the first energy level has one sublevel, the second has two, third has three, and so on. Fourth has four sublevels, fifth has five sublevels. So the further away we get from the nucleus, not only do those energy levels get closer together, but each energy level has more sublevels. So because of that then, the differences in energy between them, the further away we get from the nucleus, the difference in energy gets to be very, very small. And if now we start looking at some of these electron configurations, it turns out that there are a couple tendencies. And the tendency is this, that it turns out that the D subshell is more stable when it is either half filled or completely filled. So there's more energy stability. Now the reasons, we're not going to worry about what the reasons are in there, but if you look at them, looks like this D5 is pretty common in here. So there's D5, 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 D5. It looks like we have a whole bunch of D10s in here. So there's something about the arrangement of either entirely half-filled orbitals or entirely filled orbitals that is a little bit more stable. And likewise, if we go from something, say, like from zirconium to, what is this, niobium, number 40 to 41, we jump from 2 in the D to 4 in the D, simply because even it's not just if it's completely half-filled, but as it's approaching half-filled, it's also a little bit more stable. And that's why we might see things more like a D9 or whatever show up here, because again, that arrangement of either half-filled or completely filled orbitals is a rather stable arrangement for the D subshells. And likewise, if we go through the F's here and start looking at them, you'd see that the arrangement with 7 F electrons is also quite common. And all of a sudden they jump up from a 4F 7 here to 4F10, and so on up here to 14. So there's something that's rather stable about that arrangement of either having those d orbitals either half filled or completely filled. That's stable. Now for you, of course the question is going to be, do we have to know this on the exam? I always hear that. And the answer to that question is, well, you don't need to know the exact elements. What should you know is that there's a tendency towards either half filled or completely filled. And that obviously there's some exceptions. And likewise for the F, there's a tendency towards half filled or completely filled. So a question would be, please identify an element that is an exception to the building up principle. It might be, which one is more likely to have an exception? Now, do we find any exceptions out here in the P's? No. Do we find any exceptions in the S's? No. If we're going to find exceptions, they're going to be in the D block or in the F block. So that's what we should know. If we find exceptions, they're in the D block or the F block. And now there's another reason why we find them in the D and F. Not only is there a greater tendency towards either half-filled or completely filled, but remember now that these here are not considered to be valence electrons. When we're filling here, these aren't valence. And when we say they aren't valence, what are valence electrons?
The ones at the outer ones will determine the bonding of them.
Right. The outermost ones are the valence electrons that determine the bonding. Electrons going in here are not the outermost. These are what we call inner level electrons. So a D shell in here is not an outer level. Because remember, this here they're going to the 4s. Out here they're going into the 3D. The third energy level is not the valence shell. Here we're in the 5s. Over here we're in the 4D. So again, these electrons are not the valence electrons, nor are these the valence electrons down here. They are inner level electrons. So that's part of the reason then why we see some of these exceptions, is that we now are not putting electrons in the outer level. We start putting them into inner levels, and those, when we're putting in those inner levels, those levels are so close together, then we have to start looking at the arrangements within the orbitals to help us determine stability. Okay, so any questions on these here? All right, so if I would just put myself a little reminder in here, I might just label them like this here to remind me that this is what we predict. But we're showing in the table here, this is what they are actually. And now, as far as how we determine them based on their line spectra. We do an analysis of their line spectra to tell us what that actual arrangement is. And in terms of their chemical reactions, the differences or the exceptions does not lend to too much change in their chemical behavior. So, from a chemicals perspective, they do not behave a whole lot different. Okay, any questions that we have? All right, go on to the next page here. And the next page talks about trends in atomic radii. And this is one now that, like for you, I also have your periodic table out here today. If you did not pick up a periodic table, there's an extra one up here, extra ones on the table back there. You grab one. Now what we're looking at next are what we call periodic trends. Periodic trends. And when we talk about periodic trends, when scientists use the term period, we talk about something that occurs in regular intervals. So we might talk about the period of the moon orbiting the Earth. We might talk about how the period of a pendulum is, which again is something that if you're swinging a pendulum back and forth, the amount of time it takes for it to go out and back would be its period. And so in the case of chemistry, what we talked about occurring at regular intervals, like we demonstrated the other day, we saw that these elements right here all had very similar reactions. And if we had done the same reactions with the elements of group 2A, we would have seen the same thing. We would have seen a very similar behavior in terms of their chemistry. Or if we'd gone out here to the halogens, we'd see very common behaviors in terms of their chemistry. So That's why we call it the periodic table, is because the properties repeat themselves in a regular pattern. So we saw some of them again being their chemical properties. But there's some other things that repeat themselves in a regular manner as well, and we look at what are called trends in the behavior of some of them. First of them is in the atomic radii. So now, if we look at our periodic table, come back here and look at the periodic table, and we say, well, how many electrons does an atom of hydrogen have?
One.
That's one. That's easy. We go to something like lithium. This would have 3. We go to sodium. This would have 11. And so one would think then, as we go down within a group, that the size of the atoms would be larger. Okay? That's what we'd think. And if we went across these periods, we say, well, how many does potassium have? 19. Something like manganese has 25, and so on. The numbers increase as we go across here. So just like your reason going down here, if the radii were to increase as we go down, we should then also expect that the radii increase as we go across. Well, what does our data show? What happens? Go ahead, let's take about 1 or 2 minutes. See if you can determine what happens to the radius as you go down within a group and as you go across a period. So look at your data on page 2 there. What happens to the radius as you go down a group and as you go across a period? And once you have that, write down what you observe as a general rule. And then compare with your neighbor. As you go down within a group, what happens to the atomic radius? As you go across a period, what happens to the atomic radius as a general rule? And as a general rule doesn't mean like every single one, but as a general rule, what is the trend? Okay, what is the observation? As we go down within a group, what happens to the values? They increase. And as we go across from left to right, what happens here? They decrease. They don't increase, they actually decrease. Now, there's a reason why they do this, and it works something like this. We have to consider, and this is now a figure back on your first page here, it's something that we have to consider when we look at these. It's called the shielding effect and the effective nuclear charge. Okay, and what we're going to look at here, and this describes this. This is for the element lithium. I don't know that it indicates it right here. This is lithium. And we need to look at what's called the effective nuclear charge. And we determine the effective nuclear charge like this. We determine the effective nuclear charge by looking at what we say the nuclear charge is, which is 3 plus, okay? And then we subtract from it the number of inner level electrons, which your author here calls core electrons. So again, the effective nuclear charge is equal to, and let's write this down here somewhere, the effective nuclear charge is equal to, and I shouldn't say it's exactly equal to, it's actually an approximation as your author is showing here. It's approximately equal to the nuclear charge minus the number of inner level electrons. And we think of it like this because this is, and we call it the name effective like this because this is effectively what the valence electrons are experiencing for a charge. And it's because the valence electrons are shielded by these inner level electrons. That's what we call the shielding effect. So if you look at this valence electron out here, this valence electron is being shielded by these inner level electrons. So as these move around here, you can think of this one electron being shielded by these two electrons. Well, these two electrons then basically cancel out the effect of two protons, which basically means we have one proton, the effect of one proton left over. So again, two inner level electrons are shielding the effect of two of these protons, meaning it's still feeling the effect of one proton, which is a one positive charge. So now if we start looking at the elements as we go across a group, let's look at something like lithium, and let's draw out some figures here now. We might look at the electron configurations like this, and I'll go ahead and write them all out. We'll look at them for lithium, boron, and neon. So I'm picking 3 elements from group 2. So again, I'm picking lithium, boron, and neon. These are all elements of period 2. Now if we write their configurations, the configuration of lithium would be 1s2, 2s1. Configuration of boron would be 1s2, 2s2, and boron is in group 13, so it's going to end with 2p1. And neon is going to have a configuration of 1s2, 2s2, and will end with 2p6. Well, now if we were to draw pictures of what this looks like, it looks something like this. We're going to go ahead and draw the protons in the nucleus. So protons here, protons here, protons here. Now we need to tell how many protons there are in the nucleus for each one of these. Lithium is going to have how many protons? 3. Boron's going to have how many? 5. And neon is going to have how many? 10. Where do these numbers 3, 5, and 10 come from? Atomic number. Remember that the atomic number is the number of protons in the nucleus for each of these elements. Well, then we're going to start putting in the electrons. So now, these electrons here belong to the first energy level. These belong to the second energy level. These belong to the first. These belong to the second. These belong to the first. These belong to the second. And so now we start counting valence electrons. Lithium here has how many valence electrons?
1.
Boron has how many? 3. Neon has 8 valence electrons. So we start drawing them in like this. We want to show the inner level electrons and those valence electrons. Inner level and valence electrons. Inner level and valence electrons. So these here just represent, we're thinking of them now as orbits, even though remember that's not a completely accurate way to write them. Lithium is going to have how many inner level electrons? 2. And how many valence electrons? 1. Boron's going to have how many inner level electrons? 2. And how many outer level electrons? 3. Neon's going to have how many inner level electrons? 2. And how many valence electrons? 8. So we put in 1, 2, 3, 4, 5, 6, 7, 8 out here. So now if we want to determine the effective nuclear charge, the way we label the effective nuclear charge is like this, with a Z and a subscript of EFF for effective nuclear charge. We want to look at how many electrons are shielding the valence shell from the nucleus. So in this case here, like we already talked about, a valence electron is shielded by how many electrons? 2. So basically a valence electron here is going to see how many protons? 1. So we would then say its effective nuclear charge is 1 plus. The effective nuclear charge of Boron. These valence electrons here. Let's just we can pick any one of them. A valence electron here is going to see through or be shielded by how many interlevel electrons?
Shielded by 2.
It's still going to be shielded just by 2. So a valence electron here is going to see how many protons?
3.
3. And so again, when we say how many is it going to see, basically again, these shielding electrons or these interlevel electrons would cancel out the effect of 2 of the protons. So in effect then, any one of these valence electrons is still going to be seeing 3 protons, or it would be in effect a nuclear charge of 3 plus. What would the effective nuclear charge be for this last one? 8. And why is it 8? Well, how many shielding electrons are there? 2. There's 2 shielding electrons. That cancels out the effect of 2 protons. If it cancels out the effect of 2 protons, it's still ineffectively seeing 8 protons. Yes?
If we had another level and there was 8 in the previous one, so say it's like 2 in the third orbital thing, would
Okay.
the 2 and the 8 cancel out?
Yes, they would. So if we went on to something like arsenic, that would be a good. No, I don't want to pick out arsenic. Let's pick out one that's right below boron. Let's go from boron down to gallium. So let's say we went on to something like gallium. And before I do the gallium, I just want to point out the effect that this has on the radius. Now remember, what do opposite charges do? They attract. So if the effective nuclear charge is increasing as we go across from left to right, then the greater that effective nuclear charge, that's going to suck in those electrons even more, because there's going to be a greater attraction on those shared electrons. As a result, then, as we go across from left to right in the periodic table, the nuclei will decrease in size. Now, of course, as we start getting out to the end of that series, notice now, whether we look at this figure here or whether we look at this one here, notice now, though, as we get to the end, that difference, that huge difference begins to get smaller and smaller, and in effect here, the nitrogen, oxygen, fluorine, and neon all have about the same size. And likewise here, if you look at the sulfur, chlorine, and argon, all kind of about the same size. And that's because as we get out towards the end of a particular period, we start packing in more and more electrons, and of course what are light charges going to do to each other? They're going to repel. So the net effect then, that's why we say that this is an approximate effective nuclear charge. This is not the actual nuclear charge. If you want to know what the actual value is, there's much, much, much more complex physics that goes into it. But we approximate it then in this way to tell us the effect of the decreasing radii as we go across. So if we went to something like gallium, then we could write out its complete, I'm going to write the complete configuration for gallium. We would write it as 1s2, 2s2, 2p6. And you can kind of help me here with this. We're trying to get up to right here. So 2p6 is going to take us all the way through here. After 2p is going to come 3s2 then, 3p6 then, 4s2, 3d10 and 4d1. Or P1, right. So we come in here then, put in the 3s2, 3p6, 4s2, 3d10, 4p1. And now we want to draw a diagram of what gallium looks like. So we go to its nucleus. The nucleus of gallium would have how many protons? 31, right? Then we start looking at the different energy levels. We have a first energy level. We have a second energy level. So this is first, second. This here is the third energy level. And this here is the fourth energy level. Okay, so these here are together. These here now are together. So now if we start drawing in how many electrons are in each of the different levels, how many levels do we have altogether? 4. So we'll put in 1, 2, 3, 4. Now the valence shell has how many electrons altogether? There's 3 of them because we have these 3 right here. So we put in the 1, 2, 3. How many would go into the third level altogether?
18.
There's going to be 18 that'll go in there. Now we put in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. The second energy level has how many?
8.
8. So we put in 1, 2, 3, 4, 5, 6, 7, 8. And then the first energy level has just 2. But now if we add up all of these here in the first 3 levels, how many do we have altogether? There's 28. There's 28 interlevel electrons and 3 valence electrons. So now, if we asked it, if there's 28 interlevel electrons, that means there's 28 electrons that are shielding the valence shell. So there's 28 shielding the valence shell. Each of these electrons out here is effectively seeing how many protons? 3. Because there's 31 protons that are basically having their effect canceled out by 28 interlevel electrons. And so as a result then, we take the 31 minus 28, and we see that the approximate nuclear charge here, effective nuclear charge that it sees, is about a 3 positive. Well, of course, this effective nuclear charge of 3 positive matches that of the boron here, which also saw an effective nuclear charge of 3 positive. Basically, all of them here that are in this group right here are going to see an effective nuclear charge of about 3 plus. And as a result then, basically their radius is still going to start increasing because it's just kind of like the layers of the onion. This here are electrons in the second level, these are in the third, these are in the fourth, and so on. So they will still increase in size as we go down within a group. But they are still shielding electrons, which means that gallium is probably going to be smaller than is either the potassium or the calcium sitting out here. Okay, so any questions on these? Okay, now if you look at the D block electrons, you look at what happens in here. Notice now we see that the size starts to go down. As we approach the end of the Ds, they start going back up again. Remember now that the electrons that go into D sublevel, these are not outer level electrons. These electrons are inner level electrons. Because they're inner level now, we're starting to pack more and more electrons into inner levels. And as we start packing more and more into inner levels, what do light charges do? They repel. Okay? And so what will happen then, if you count this, this is D1, D2, D3, D4, D5. We get to D6, and it looks like once we get right around here then, we start putting that second electron into those d orbitals, then that size begins to increase because then the repulsions start taking over on the inside and begin increasing that size. But then when we start putting these electrons back in here out in the valence shell, then the size then again begins to decrease because as we go through here, the effective nuclear charge begins increasing again. Effective nuclear charge in all of these in the center here. All of these here have the same effective nuclear charge, approximately. And what is that approximate nuclear charge going to be for all of them? Approximately. Well, we have to go back to those electron configurations. Go back to the electron configurations. If we go back to the electron configurations, pretty much all of these that are in this block here have how many valence electrons? Pretty much have 2 valence electrons. And we can tell that because 4s2, 3d1. 4s2, 3d1. Notice that the number of valence electrons is staying pretty much constant here now. I have S2, S2, S2. Here's an S1, S2, S2, S2. So pretty much all of these here have 2 valence electrons. So that means that all of them here in the center are going to have an approximate effective nuclear charge of about 2 plus. And again, because of that reason, they all have about the same size. And again, because of the fact that we're filling them up and then we start doubling them up right about here, we start seeing those sizes increase again due to an increase in repulsions that will tend to push out the size of that atom. Any questions on that? All right, next page in your packet. Looks like this. These are ionization energies. Ionization energies. First thing I'd like for you to do, these aren't just ionization energies, these are first ionization energies. Let's talk about what an ionization energy is. What is an ionization energy? We say that ionization energy is energy right here. This is the energy required to remove an electron from an atom or ion in the gaseous state. And we have what are called first ionization energies, second ionization energies, third ionization energies, and so on. This particular table here shows the first ionization energies. This here shows the first ionization energies. And what the first ionization energy is the amount of energy to remove the first electron. The second ionization energy is the energy required to move the second electron. The third ionization energy would be the energy to remove the third electron, and so on. So what I'd like for you to do is this. Take about 2 or 3 minutes, maybe 5 minutes. You're going to look at these 2 figures right here, and then jump to the next page and look at this figure, and look at these labels. IE sub 1 is the first ionization energy. I sub E2 is the second ionization energy. IE sub 3 is the third ionization energy, and so on. Fourth ionization energy, fifth ionization energy. So what I'd like you to do is these things. First of all, determine the trends as you go across the periodic table from left to right for the first ionization energy. So determine the periodic trend as you go across from left to right and as you go down within a group. So again, determine the trends as you go across from left to right and down within a group for the first ionization energy. Then see if you can explain the reason for that. And then move on to this table here. And now notice these big jumps. Why the big jumps here in this division between these colors? So see if you can explain the big jump between these. So I'll give you about 5 minutes here to come up with the trends, and then see if you can explain the trends and explain these jumps. Okay. When I say the trends, it's not that everyone follows the rule. You want to look for most of them following the rule. Again, what are the trends as you go down within a group? The trend as you go across from left to right. And see if you can explain it. I'll give you a hint. If you're having trouble comparing the trends, ask yourself, how do the trends compare to the atomic radii? There's your hint. How do the trends you just observed compare to the atomic radii? How do the trends of ionization energy compare to the atomic radii? Take another minute or two. All right. All right, let's look at the trends. First, ionization energies. As we go down within a group, what happens to the values? Do they increase or do they decrease as a general rule? They decrease. As we go across from left to right, what is the general rule here? They're going to increase. And how do these trends compare to the atomic radii? As the radius gets smaller,
Requires more energy to remove the first electron.
Exactly. So as the atoms get smaller, it requires more energy to remove that first electron. Can anybody think why decreasing the size of the radius would cause there to be more energy to remove an electron? It has to do with attractions, exactly. Remember? Right, opposing charges. There's attraction between the negatively charged electrons and the positively charged nucleus. So as that effective nuclear charge increases, it is more difficult to remove those valence electrons. It takes more energy to remove them. So what you need to learn first then is effective nuclear charge. Once you learn the effective nuclear charge, and this is within a group, because the group is the hard one, not the group, within a period. The groups are easy to explain. I hope you realize that, because as you go down with the group, that's the one that makes sense. If you go down within a group, remember that the radius gets larger and larger. It gets larger and larger because within a group, the effective nuclear charge basically stays the same. And you're adding more and more layers. And if you're already starting with an electron that's further away from the nucleus, it's going to be pretty easy to remove it. If it's closer, it's going to be more difficult to remove that. So the one going down should make sense all the time. What's going to be more difficult is to figure out what's happening in a period. And what's happening in a period then, remember what happens to the effective nuclear charge as you go across from left to right? Values increase. Because the effective nuclear charge increases, that makes the radii smaller. So it makes it smaller, that makes first ionization energy larger because it takes more energy then to pull those electrons out of the atoms. So any questions on those trends? Okay, then the big jump. We go on to the next page. There was the difference in the colors here, and I know yours is gray and gray. But if you look at them here, we go from sodium, first ionization energy, to second ionization energy, a huge jump. Magnesium, these two, they increase a little bit, then a huge jump. Aluminum, these increase a little bit, then a huge jump. Why the big jump here in the division? Right, we are now going back to the core electrons because in the case of aluminum, how many valence electrons does aluminum have? It has 3 valence electrons. So if you get rid of those 3 valence electrons, they're all in case of aluminum, they are in the 3rd energy level. We now remove all 3 of those electrons in outer energy level. That 4th electron now is going to be an inner level electron. And because now that charge is going to be so much larger, the effective nuclear charge, it's going to be that much more difficult to remove those electrons from that what is then now the new valence shell. So that's the thing we want to point out here, is that huge difference. Ultimately, what this is leading to is that we're going to talk about why the arrangement of the valence electrons of having a noble gas configuration is so important. When atoms bond together, and this is going now into chapter 9, it's kind of a bridge here between 8 and 9. It turns out that when atoms bond with each other, they like to acquire what's called the noble gas configuration. And it's because once we get to that point then, we're working backwards from aluminum, we take off the 1, 2, 3 electrons, and now it has the same electron configuration as neon, and those electrons are a lot closer to the nucleus, and it's going to wind up being a much more stable arrangement. But before we do that, any questions that you have on this? Okay, and the last table that's on here is what's called the electron affinity. We say that the electron affinity is the energy change associated with gaining an electron by an atom in the gaseous phase. Now, if you start looking for trends here, there's not any really clear-cut trends other than these here happen to be super negative in values, which means that if you try adding an electron to each one of these out here, it's going to wind up giving off a whole lot of energy. And if we look for trends, there's not as clear-cut of a trend for the electron affinity as there is for the ionization energies, but we can say at least that these here give off plenty of energy for the simple reason that these wind up forming stable ions when they do so. They wind up filling that outer level. So with this then, where we're going to head into is, it's kind of a blend. I think your text puts it into chapter 8. And so we're kind of looking at the end of 8, beginning of 9 here. I want to look at what happens in ion formation. And we're going to look at what are called isoelectronic species. Now, before we go ahead and talk about isoelectronic species, we should probably analyze the word. The prefix iso means the same. So like if you have an isosceles triangle, what is an isosceles triangle? Two of them have the same side, right? And if you're in meteorology, you might talk about isobars, which is where you go across. These are of equivalent temperatures across on the map. So isoelectronic means that these are ones that are going to have the same number of electrons, or they're going to have the same electron configuration. Well, let's work with these two elements right here. We're going to work with sodium and oxygen. And let's write out the electron configuration for the sodium and the oxygen. It'll be helpful if you have these in pencil. If you have them in pen, you're going to have to cross some stuff out, which is fine. Let's write the complete electron configuration for sodium and oxygen. So for sodium has the electron configuration of 1s2, 2s2, 2p6, and it's going to end with 3s1. Okay. If we go to oxygen, its configuration is going to be 1s2, 2s2, and 2p4. Now, at this point, these are not isoelectronic with each other. Just to be clear, these are not isoelectronic. But what we're going to do now is we're going to show the common ions that are formed. Now, go back to when you did your nomenclature. What is the normal ion formed by sodium? +1. Common ion formed by the oxygen? How many? Right. Now, in case you don't know the convention, it's not clear. There's a reason why I put the number in front. You always put the number in front of the sign when you want to show a charge. So you actually say it's 2 minus. So if you want to talk about a positive or negative number, you put the sign in front. But when you want to talk about the charge, you put the number in front with the sign behind it. Okay, and it will be particular when it gets to the ACS exam. So if you don't know that, reminding you now that you do need to make that distinction between them. So the number out front of the sign means you're looking at the charge. So now if we're looking at the charge, we need to see what this implies. If we have a single positive charge, what does that mean has happened to the number of electrons?
The lost one.
Lost 1, exactly. So this goes away, and we have this configuration right here. So again, we're basically getting rid of this, and this winds up being the configuration. And then 2 minus means that what has happened?
Gain 2 electrons.
Gain 2 electrons. And so the configuration of the oxide ion, I guess I'll leave it in here for those that want to look, looks something like this. And now we say that these two are isoelectronic with each other. A sodium ion and an oxide ion have the same number of electrons. Not only do they have the same number of electrons, but they have the same electron configuration. Now let's look at what happens to the size of these. And it should make sense. If we take electrons away, what do you think is going to happen to the size of a sodium ion compared to a sodium atom? Sodium ion bigger or smaller? Smaller. You take the electrons away, definitely going to be smaller, because actually we're taking away a whole shell on this one. Okay, so it should make sense. And then if we look at the oxide ion, we now added in 2 electrons, so its size is going to be bigger. Say, well, wait a minute. Remember when we were going across from left to right before, we were talking about the atomic radii, we said when we were looking at the atomic radii that the radii going across got smaller and smaller. Okay, well, what happens here with what we call ionic radii is something a little bit different, and we still have to go back and look at them in terms of effective nuclear charge. So by effective nuclear charge, we need to look at how many protons there are in the nucleus in each one of these, and the number of electrons. So how many protons will be in the nucleus of a sodium ion? And how about in an oxide ion? It's going to be 8. Okay, so now we start tracing those electrons out here. We have the first energy level, we've got the second energy level. First energy level, second energy level. We start putting those electrons in. How many will go into the inner level here on the sodium? 2. And how many in the outer level? We'll now have 8 going in there. There's 5, 6, 7, 8. We go to the oxide ion. Inner level is going to have 2. Outer level will have 8 as well. So now we start looking at the effective nuclear charge. We start looking at the effective nuclear charge. The effective nuclear charge here on the sodium is going to be how many?
8.
I hear 8. Is that right?
That's right.
Well, let's see.
9.
It's going to be 9 because we have 11 protons, and these outer level electrons are being shielded by 2 inner level electrons. So basically these two will cancel out the effect of 2 protons. So its effective nuclear charge here is going to be 9. So write it as 9 plus. The effective nuclear charge on the oxygen, or the oxide ion, is going to be
6 plus.
6 plus. Okay, so now, since this is a 9 plus and this is a 6 plus, If we now have to compare these two isoelectronic species with each other, which one is going to be smaller? Start looking at them. What do opposites do? They attract each other. Which one is going to exert a stronger attraction on the valence electrons?
Sodium.
Sodium will. And if this one exerts a strong attraction, this one should be smaller than is this one over here. So then if you go to your last page, no, this is not the last page, this is probably your insert then, and we look at those effects, then make the comparison, you should then be able to compare something like the sodium ion, and I know that your text there is a little bit small, but you could then see, if we go from a sodium atom to sodium ion, you see by removing an entire shell, we wind up with a sodium ion that is much smaller than the corresponding sodium atom. This goes from 186, I believe this is picometers, down to 95 picometers. And then if you compare that over here to the oxide ion, which I think sits up right here. So we're basically comparing these two. By adding on those two extra electrons, the size is increased. And part of the reason why it has increased now is because we add on those extra valence electrons. Electrons now are going to have more repulsions for each other. Because they have more repulsions, then that's going to cause the size of that oxide ion to be larger than the corresponding oxygen atom. In terms of size of these two now, if we compare the ions, we see about 95 picometers here for the sodium ion versus 140 picometers here for the oxide ion. So we're comparing these values right here. So again, these are called isoelectronic. They are called isoelectronic because they mean the same number of electrons. When you start looking at the same number of electrons, you need to look at the effective nuclear charge to help determine which of those two isoelectronic species is the larger of the two. So, any questions that you have on these? Any questions? All right, then. We're going to wrap up here by looking at electron configurations of ions. We've already looked at a couple of them here. Any questions on how we come up with the electron configurations for these two ions? Okay. Pretty much all of the S block and P block then are handled in the same way. So if they're in the S block, these are going to be metals, and the metals are going to always give up electrons. The nonmetals that are part of the P block will always wind up gaining electrons. Let's look at something like tin. Tin, Sn. So if we want to write out the electron configuration of tin, we can then show the configuration of tin being something like this. Now let's do shorthand configurations. To write out the shorthand configuration of tin, we go back to the previous noble gas, which is krypton. And once we go back to the noble gas configuration of krypton, we then add on 5s2, 4d10, and 5p2. When you write out its configuration, you should always confirm that the sum of the superscripts does indeed add up to be the atomic number. So krypton represents 36, and this here is 14 more. 36 plus 14 gives us 50, which matches the atomic number of tin. Now tin forms two ions. Anybody know what the two charges of tin are? 2 plus and 4 plus. Exactly. Now to get the configuration of the ions, what happens is that the highest energy electrons are always removed first. So if we get 2 plus, what is the highest in energy between the 5s and the 5p? Well, remember the complexity of the shape. Are s orbitals more complex or are p orbitals more complex? P's are more complex. So if we want to form a 2+ ion, the electrons that are removed first are the P's. And so its configuration is 5s2, 4d10. See if you can come up with the electron configuration of the tin 4 ion. And once you get that, go ahead and do the zinc ion and do the configuration of the iron 3 ion. Iron 3 ion. Write out these configurations. Now the tin is not complete. Let's see if you can write out the configurations of these two, or I guess these three. And once you get them, compare your answers. Now, I know you want to look off that front page that you have here, but if you want to practice exam-wise, you probably should be looking off of this periodic table here. This is the one you're going to get on your exam. We're going to write on periodic tables one more time today, so who needs another periodic table? Anybody need one more? Anybody need one more? We're writing on them again next activity. Need one more clean one. Okay, let's finish these off. The tin 4 ion would be the krypton in square brackets followed by 5s2. Zinc. Square brackets would be Ar followed by 4s2 or 3d10 or both.
Both, yes.
Okay, we're looking at zinc ions. What's going to disappear in zinc ions? 4s or the 3d? 4s would be, because if we went to zinc, zinc would start by looking like this. And which electrons go away first? The outermost. And which ones are the outermost? The 4th. So we get rid of these. And this would be the electron configuration of the zinc ions. And for iron 3, it's argon followed by 3d, probably not 5, or is it 5? 1, 2, 3, 4, 5, 6, it would be 3d5.
Why is SN4 plus
Yeah.
5s2?
Excuse me?
Why is the tin 4 the 5s2?
Yeah.
Why is it the 5s2?
We lost 10 electrons.
Oh, which one should it be? 4d10. There you go. Yeah, why didn't you tell me that? All right, 4d10. All right, any questions? That's why you were kind of gun shy. Okay, any questions on these? Okay, then the last thing we're going to look at here today is going to be Lewis diagrams. Lewis diagrams. And by the way, when I write these out, I'll put these on the next page here. Lewis. I'm going to write down about structure, diagram, symbol, and formula. And the reason why I put this down is because, oh, you know what? Sometimes I put this electron over here, I think. And you don't need to worry about this. The reason why I'm just doing this is here. Turns out we've not standardized our vocabulary for what we're looking at next. basically if you take any word out of the first column, choose to maybe take one out of the second column, and then any word out of the last one, they all mean the same thing. So a Lewis dot structure is the same as a Lewis symbol, which is the same as a Lewis electron dot diagram, the same as a Lewis dot formula, a Lewis formula. They all represent the same thing. So if you basically see the word Lewis at the beginning, followed by any one of those words at the end, they all mean the same thing. Okay? So that's what we're looking at next. And you're going it doesn't mean that I don't know what I'm talking about. I'm not intentionally changing the names. It's just something that the chemists, we've done a bad job of standardizing the vocabulary. But what this Lewis diagram does is this. It basically is the atomic symbol surrounded by dots. It is the atomic symbol surrounded by dots. And the dots represent the valence electrons. Now, what is the most valence electrons we can have? 8, exactly. And it's 8 because if we looked at something like krypton, for example, we wrote out that configuration of krypton, we would have for krypton, I'm going to write out the complete thing, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, which is the 36 electrons. And if after krypton we would then went on to rubidium, what comes after the 4p6? Rubidium is going to end with 5s1. So if we went on to rubidium, be 5s1. Well, you see what happens here is that before we got to rubidium, we have how many valence electrons right here?
8.
We have 8. Then if we add on one more, we now no longer have 8 valence electrons. We go back to 1. This happens every time we get up to noble gas. The next one then belongs to the next higher energy level. So the most valence electrons we can ever have is 8 valence electrons. So for that reason, on our periodic tables, we would write a Lewis symbol for an element of group 8 as having 8 dots. And the convention for writing the dots is we place one dot on each side before we double up. So then on group 17, this one here would have 7 dots. I'm going to put another table in here. So we have 8 dots here. We got 7 dots here. Then we basically just work backwards. 6 dots. And now don't spend a lot of time worrying about what side you double up and which side you don't, because they all represent the same thing. We should think of it as a top and a bottom and a left and a right. And so whether I show the 5 dots like this for this group here, or whether I double them up on the top, doesn't matter. They all represent the same thing. Or if I double them up on the right-hand side, they all represent the same thing. So we keep working backwards here. We get to group 13. We're showing 3 dots. Turns out that we do not worry about the transition elements. And we go back here to the A groups, which would have 2 valence electrons here for group 2A and 1 valence electron here for group 1A. Most of these that are in the middle here, these here will mostly have 2 valence electrons, as we've already seen. So that's mostly 2 valence electrons. But we typically do not write Lewis structures for the transition elements. So then, if we wanted to write a Lewis diagram for a particular element, let's say we wanted to write the Lewis diagram for phosphorus. We'd write the Lewis diagram for phosphorus by writing P with 5 dots. If we wanted to show it for calcium, we'd write Ca with 2 dots. And the only exception to all of the A groups would be which element? There's only one element that does not follow this in all of the A groups. Which element is it? helium right here. And helium's configuration is 1s2. So we write the dots for helium. We actually show 2 dots. And this one we show them doubled up. And we show them doubled up in helium because they are paired up in that one atom of that element. So that's it here for today. Any questions that you have? If it's calcium, you do not double them up. It's 1 dot on each side before you double them up. All right, that's it, folks.